everyone, and welcome to the chapter on Introduction to Logistic Regression. In this lecture, we will discuss classification problems, how to use logistic regression to solve them, and also how to interpret the results of logistic regression. So moving along, we want to learn about logistic regression as a method for classification. Some examples of classification problems are spam versus ham emails, lone default yes or no, disease diagnosis. Above all are examples of binary classification. When we say binary classification, it can have only two values, 0 or 1, yes or no, hot or cold, something like this. So the logistic regression produces results in a binary format, which is used to predict the outcome of a categorical dependent variable. So the outcome should be discrete or categorical, such as zeros or ones, yes or no, true or false, high and low, etc. So here we try to decide on which of the categories a new observation belongs to. So here, for example, if we see disease diagnosis, we can classify if someone has cancer or not, or someone is diabetic or not. So far we have only seen regression problems where we try to predict a continuous value. Although the name may be confusing at first, logistic regression allows us to solve classification problems where we are trying to predict discrete categories. The convention for binary classification is to have two classes, 0 or 1. So we can't use a normal linear regression model on binary groups. It won't lead to a good fit. Looking at this graph, just imagine that we are trying to predict the likelihood of paying back a loan, which is expressed as probability. So here, the lowest mark is the 0, which means that there is 0% probability to pay back the loan. This is 20% probability of 0.2, assuming that probability is always between 0 and 1. 0.2, 0.4, 0.6, 0.8 and 1.0. So this one at the top means that it has the probability of fully paying back the loan. So assume that this x-axis is some sort of a paycheck value, which would mean that if your paycheck is lower, you have 0% probability to pay back your loan. And as your paycheck is higher, you will move towards higher probability and probably 100% to pay back the loan. So you see this yellow marked line either marked at 0% or 100%, because this is on the training data. And so if this was training data and we are trying to use the linear regression model fit, we would actually land up predicting very bad values. Somewhere the values might even go below 0% probability. So instead, we can transform our linear regression to a logistic regression curve. A logistic regression curve will always go between 0 and 1. The sigmoid, a logistic function, takes in any value and outputs it to be between 0 and 1. So this sigmoid is going to be the key to perform logistic regression in order to perform classification. So here we are defining this sigmoid function as theta of z, now z is just referring to the x-axis, is equal to 1 over 1 plus e to the power of negative of z. So no matter what value you give to the z here, you will always get a value between 0 and 1. This means that we can take our linear regression solution and place it into the sigmoid function, because it is always going to be between 0 and 1. And that is going to look something like this. Remember, the linear model is y is equal to beta 0, which we discussed it as a constant, plus beta 1 into x. Here it is b0 plus b1 into x, which is the linear model. And we give the logistic model as p is equal to 1 over 1 plus e raised to the power of the linear negative of the linear model, which is minus of b0 plus b1 into x. So here if you see, the linear model is this blue line, which is the regression line, and the logistic model is between this 0 and 1, given as p. So this is how we transform our linear regression into a logistic model. So the basic premises here is that this results in a probability from 0 to 1 belonging in the 1 class. So which means that we can set a cutoff point at 0.5 exactly between 0 and 1, and we can say that anything below this cutoff point, this red line, results in class 0, and anything above is class 1. So this is the cutoff point marked in red here, and anything which falls between 0 to 0.5, we can say it belongs to class 0, and anything which falls between 0.5 to 1 belongs to class 1. So when we say binary classification, we can say that anything which has a probability of 0 to 50% could be class 0, and anything above 50% belongs to class 1. So after you train a logistic regression model on some training data, you will evaluate your model's performance on some test data. And you can use a confusion matrix to evaluate classification models. A confusion matrix is a table that is used to evaluate a classification model on test data. Here, the true values are already known. So let's try to understand through this example. We have a binary classification example here. So in this example, we are trying to predict the presence of a disease. No is a negative test with false equal to 0, and yes is a positive test with true is equal to 1. So here we have predicted values here on the as a column, and the actual values which we already know as rows here, and these are some intersections. So we tried to analyze data for 165 people. So here yes would mean that they have the disease, and no would mean that they don't have the disease, and this is predicted and this is actual. Let's see how we can interpret this. So here, out of 165, they classify predicted yes 110 times and predicted no 55 times. And in reality, which is the actual, 105 patients have the disease and 60 patients do not have the disease. Now let us look at some of the basic terminologies in the confusion matrix. We have something called true positives, true negatives, false positive, and false negatives. Let us see what this means in this particular table. The true positives are the ones where we predicted yes, and in reality also the value is yes. In this case, we predicted that the person has the disease, and in actual also the person has the disease. So here we predicted 100 people have the disease, and the actual also says the 100 people had the disease. So this is a true positive quadrant. The true negatives are the ones where we predicted no, the people did not have the disease, and reality also it predicted it says that people did not have the disease. So we predicted 50 as a true negative, and in reality also it is 50. So the false positive is where we said they have the disease, we predicted they have the disease, and in reality they do not have the disease. This is also known as type 1 error. The last one is false negatives, where we predicted no, they do not have the disease, and in reality they had the disease. That's known as a type 2 error. So then we calculate the accuracy and how often is it correct. That is what it means. Now, how is it given? The formula for accuracy is given as true positive plus true negatives divided by total. In our case, we had 150 as true positives plus true negative is 100 plus 150, 150, and total observations is 165, which evaluates to 0.91, which means that our model is 91% accurate in this case. Then we calculate the misclassification rate, which means overall how often is it wrong. So this is calculated as false positives plus false negative divided by total. Here we have 10 plus 5, 15 divided by the total 165, which is 0.09. So overall there is a 9% error rate, or we call it as a misclassification rate. So here is a funny way to remember type 1 error and type 2 error. So in this case, you're telling to a man that you're pregnant, but in actual, he is not. So this is a type 1 error where the prediction says you are pregnant, and in actual, you are not. And a type 2 error, which is false negative, the doctor says to a pregnant lady that you're not pregnant. So this is how you can remember the type 1 and type